Hello everybody, welcome to this tutorial in Transform 2022. It's what is MC with Miguel de la Varga and Jan from the GemPy team. So this event is part of Transform 2022, part of our virtual festival of digital geoscience, all free, all open access all week. So many thanks to CurveNote for sponsoring the conference. And you can find the whole schedule information at software.underground.org. Sorry, softwareunderground.org/transform. And also join our Slack channel at softwareunderground.org/Slack. Remember, if you're watching this live, you can pause and rewind the video as much as you like or as much as you need to stay up in sync with what you're doing locally. And please share it, like it, and subscribe to our channel. Now, great. So we're going to learn all about MC today, and I'm going to hand over to Miguel.
Yeah, thanks, Steve. It's great to be here another year. So first, a bit of a disclaimer. So this year we are on the road. So at the moment, I'm in a hotel. The internet sometimes goes away. So we didn't want to cancel the tutorial because it would be a pity. So we are really trying to just make it live, but there is a small chance that things go south, and then we have to just wait for us to make an async video. So eventually the video is going to be in YouTube. Let's try at least. So I don't know how many people are following now on live. We are checking Slack. So if you have any question, any comment, just let me know in the Slack channel that Steve just mentioned, so which is basically T22 Monday MCMC. So here I've been just placing a bunch of links this morning and right now. So if we click to the first link, we can see the repo, which is here, GemPy workshops. I mean, today we're going to be using a bit GemPy, but not much. But I just have this repository with all the workshops that I've been doing in the last years. So I just upload it here. So in this repository, workshops Transform 2022, you can find the Jupyter notebook that we will be playing with. And the problem this year we had is that some of the functions that we are using to get these nice plots, I wrote them a few years ago. So now the environment is a bit old. So has been a bit messy. So ideally you will have in any environment that you have GemPy installed, the only, oh, good point. Sorry, I was not sharing my screen. There you go. So I was, yes, very fast. I was just coming here to the Slack channel and just clicking in the first link that I added, which takes us here. So what I was mentioning is this is the notebook that we are going to use. And I was talking about the environments. And so any GemPy environment that is working, and for anybody, maybe later, if they really want to have a working environment, they can follow the steps of how to install GemPy from the previous transform, for example. And then the biggest difference is the pandas version. And so here we are using a relatively old pandas, so 1.2. At the moment, they're in 1.4. And also the matplotlib 3.2, it was important. So because the environment was a bit weird this year, and I think that it was not worth just going through all the installation steps to install an environment that is basically deprecated already. So we were just trying to set up the cloud solution for that. So here we have this link, labsazure.com register. So if you click there, it will just send you into a website where probably you have to log in with a Microsoft account. That is a bit annoying. But once you are there, you will have just a virtual machine for you. There is one button to just set the password of your virtual machine, and then opening your console and using this type of tunnel. So basically, once you set the password, there is a button, like a small computer button, that you can just press, and it's going to give you a string very similar to this. So if you use this, you will just connect. Actually, maybe I can try. I mean, I'm a bit afraid that because I'm logged, it's not going to work, but I will just try. So if you click in the link, it's going to bring here to register for your lab. Well, unfortunately, this is a bit taking too long. Anyway, so ideally you will just get into a place where you can just set, yeah, here, exactly. So here you have your computer. The first time that you click on that, is going to ask you to set the password, and the second time is going to give you a string very similar to this one. But in that string is not going to be this argument here, this L888 localhost 888. So that is important to just forward the port of the Jupyter notebook. So to your string, you have to add this piece in your console, and then just copy and paste in your console, and then it's going to be just connecting to the cloud. And once you're connecting to the cloud and you enter your password, if you just type Jupyter notebook, it's going to run the usual stuff of the Jupyter notebook that I can see, and then you can just copy the address, put it in your Explorer, and there was someone.
Yeah, in the SharePoint thing.
Oh, okay. Yeah, so the SharePoint, I will try to share it in a second. But so yeah, so finishing the stuff of the Jupyter Lab. So once you are able to connect, then you can just type Jupyter Notebook, you just copy the address of the Jupyter Notebook in your Explorer, and then you just have an environment with the repository that we saw ready to run. I know it's a lot of steps. I don't want to do it on live because I'm not sure how many people is going to try, but just try going forward. And if you have any question, just write it here in this Slack channel, and we will just try to get you up to speed. And the good thing is that once you are able to get inside, then it's easy to start following. Okay, sharing the link. I'm going to try again, because maybe that link was somehow broken.
I come to a sign-in page.
Oh, wow. What the hell did that? Yeah, doesn't matter. I mean, so the SharePoint, I will just share it. So I wanted just to give you access so that you could just go back. I will try to just leave the link after the course so that you can just see there the notes. But that's going to be just a couple of sketches just to help with the course. Okay, I think that's basically all the housekeeping I had for today. In any case, I mean, so all of this I'm saying if any of you really feels like following along. So I was just giving a couple of options. If you have a GemPy environment, maybe you can just set it up with the specific versions. Otherwise, just trying to set the lab Azure. But mostly this course is going to be theoretical. So you can just pay attention and follow the ride, and we can just keep doing this together. Again, if you have any questions, just interact. Otherwise, I'm going to just start with the workshop. Any comments in the Slack?
Not yet, apart from the one of the SharePoint.
Okay, so now getting into the content. So the topic of today is going to be what is a Markov chain Monte Carlo. So I just want to try to give you an intuition about this. I don't want to get into the math because it's really daunting, and many people is scared of it, and that is not for it's not so complicated. So my main goal for today is just using a couple of examples, geology-based, do a simple cases, looking at some nice plots, so that you can get a bit the gist of when using Bayesian inference and then a Markov chain Monte Carlo to solve that inference makes sense. In the notebook that we prepare for you, Jan has been writing quite a bit of content so that later you can just try to go through it and try to follow. During the presentation, I'm going to just skip a bit about it, but here a bit theory, very scary quotes about famous people. So MC generates samples from the posterior distribution by constructing a reversible Markov chain that has its equilibrium distribution to the target posterior distribution. So that's even me, that I've been doing a PhD about this topic, cannot follow very good. So again, I'm going to really just trying to bring it to the essential, when it makes sense to use it, and what is useful for. Because actually in geology, there is a lot of uncertainty in our data. There is a lot of difficulty correlating different data sets because they are so of different nature. All of this is going to help us to just do it in a more formal way. So just trying to put numbers in many of the guesses that we are, as geologists, doing all the time. So yeah, I'm going to start with a bit drawing here. So this is going to be our first case, and we are going to be building on the complexity on top of this case. So let's imagine just a group of students that we just go to an outcrop, a very large outcrop, and then we are going to end up with 3 groups of students, but now in the first case, we are going to just start with one single group of students. So we arrive into the outcrop, and the first question is going to be very simple. What is the length of this layer? So basically, this length from these 2 interfaces. Simple question, but here we can start really, when you get into the gist of that question, can get really interesting. So there are different ways that we can do this. So we can really just take the students and ask, okay, so yes, by eye, so what is the bulk of this distance? Do you think that is 20 meters, 2 kilometers, 10 centimeters, 1 meter? I mean, even just like that, without using any device, just being there and trying to guess, there is limits. So there is the distance of the Earth to the Sun, to the distance of a transistor. The thickness of this layer is going to be somewhere in between that. So yes, by reasoning a bit about the question, that is already giving us some information. So it's not from minus infinite to plus infinite. So that as humans, we are doing this type of guesses all the time. But obviously, we have more tools than that. So we can really just try to go there and measure. That's what any of us will do. But I mean, again, let's imagine in this example, I don't know exactly which number I wrote in the notebook. Yeah, 2 meters 12. So we sent a student, is 2 meters 12, so it's pretty large. So and it's very bumpy, the place. They have the device that they are using, so yes, measure tape is not super precise, but one of these students goes there and starts measuring, and after a couple of minutes, he gets the value 2 meters 12. Now, in a different context, we could say, okay, that's our answer. That's 2 meters 12. But if I asked you now, how much do you trust about that? So how much money would you put that is 2 meters 12 and not 2 meters or 2 meters 20? That's a quite interesting question, because in the end, an observation is an observation, and many times a data point that we are getting from the field, we assume that is true. But in the moment that you have a bit of context, and you know that the one who went to measure was Jimmy, who is not very good with devices, and so you hear what he's telling, but your confidence is not 100% on that. And here I'm just trying to make it a really extreme case, but the point that I'm trying to bring home is that even observations, that is the best data that we have of reality, they are biased, they have problems, and you cannot give them 100% confidence. And here we are talking about an observation that you can just look directly. So when we are talking about a log of a borehole 2 kilometers underground, this uncertainty is getting more and more extreme, also on the observations. So this is the story of Jimmy and the ruler. How we put this into numbers. So in these examples, I'm going to be going a bit backwards. So first we're going to make the probabilistic model, and then we are going to start using a bunch of plots to understand what we have done. So the library that we are using for this, and actually I'm going to start importing things, is PyMC3. So PyMC probably is the de facto library for Python. So it's written in Fiano as well. So the people who has been following me, my GemPy tutorials previous years, they know that GemPy is also written in Fiano. So the reason why GemPy is written in Fiano is because of PyMC3. Because in my PhD, I wanted to do Bayesian inference all in the probabilistic context. So today, in the last example, we are going to use a bit GemPy just to scale a bit the complexity of these models. But in this case, it's just for a bit for fun. All right, so we just have imported our bunch of libraries. Now we are just defining a couple of arrays. So the first one is thickness of observation. So this is the observation that I just mentioned. So here we have another list that is, okay, let's send all the students that we have. That is 12 students to do the same measurement. And actually they give you slightly different values. So that's already giving you some feeling that 2.12 is not perfect. But anyway, so here what we are going to try is to formalize all of this and try to just get all this information in a mathematical consistent way. So yeah, let's try to make our first probabilistic model, very simple model. So in PyMC3, so in Bayesian inference in general, and here we have Copilot just spoiling the whole exercise. The future is amazing and scary at the same time. So Copilot, for those of you that you don't know, is this artificial intelligence that auto-completes code. But yes, as Copilot knows, so in all Bayesian inference, there is basically 2 steps. So one is the definition of the model, and the second one is the inference itself, and then the analysis of the posterior. That's also an important, so the analysis of the results. The good thing of this is that they are quite decoupled. So we can just do our function and our code to define the model, and then do the inference, and then just do the whole plotting. So now we are going to just put into numbers basically the discussion that we were having before, of having one observation, and also just having to give a range of possible values to the measurement. And this is the case of one observation. So first we have to define our prior. So the prior is basically the first case. So what I was saying before, that this thickness has to be somewhere between the distance between the sun and Earth and a nanometer. So you can just be as narrow or as wide in your guesses as you want, as long as you know what you are doing. So in the end, that is a way that we are encoding information that is in our head and is completely reasonable. So saying that the fact that I said before is completely logical and coherent. There is not going to be a thickness in Earth that is larger than the distance from Earth to to the sun. So with priors, there is a lot of discussions. How do you know what do you have or which values you have? There is a lot of good content in the internet why priors are important and actually necessary, because if you don't use priors, you are really overrepresenting super large numbers, because infinite is very large. So I'm not going to get into all of that, but I'm just saying that, yes, giving a reasonable range to the values that we are studying, what is reasonable is up to you. It's an important step. Anyway, so the way that we define the priors is basically with probability distributions. So the best way of representing guesses and uncertainties is probabilistic functions that basically just gives you the probability of samples, of sampling specific values of the probability. So in this case, I'm not, again, the goal of this course is just giving an intuition, so I'm not going to get into super detail of these things. So we are going to define a normal distribution that describes our prior guess of how much is the thickness, and then we will just do the likelihood function with the observation that we have. So the first step is just defining what is the mean value. Yeah, actually these values are right. Wait, I'm going to just give it a bit of an enriched text for later. So what these specific values that I'm writing here means, we are going to see it in a second with the plots, but it's better to do it like this. It's really scary because it's using exactly the same numbers that I wrote. So maybe it has already read the repository and knows what's coming next. But yeah, thickness observation. So this is basically how we define a Bayesian inference. So it's going to be always looking like we define our prior with a bunch of distributions, and eventually it's going to come one distribution that has this argument observed, and observed is going to be an array. So this thickness observation, if you remember, it is basically this list. Good. So this is the most basic. Oh, I have to run it. So this is the most basic model that you can just define. So let's see if it's running, because at the first time that you run it, it's here not doing its compilation, so it always takes a bit longer. There you go. Yeah. So I'm not sure what I was saying, sorry. So I will just keep going. So this is the model that we have defined. And now, as I mentioned before, the next step is sampling the model. So PyMC has, so maybe I should say some words about the syntax is with. So PyMC is using this with syntax to basically just define a model, and then everything that you have to define, the definitions of the priors, likelihoods, and also the sampling is happening under this. So this single point variable is defined here, and it's basically creating a class under the hood, and we just keep using it here. So now we can, just in this cell, sample the model, which again, all of these, so now you just get a bit the gist of the syntax. All of these I will explain later with plots. What means prior, what means the posterior, what means sampling. So sample prior. Trace of the posterior. Is there any question about this? I mean, I'm going a bit backwards, so I can imagine that people is very confusing, or very confused at the moment, but it's going to pay off. Yes, give me a sec. So this is going to be the sampling stuff, and actually I'm going to just get this. And add it into the next. So now basically we are just doing the MCMC stuff. And again, I will promise we will see later, but this is just an integration that will happen there. And now that we have already our results, so we have our simulation, we can just do exactly this. To just use RVids. So RVids is another library that we're going to use. So before it was part of PyMC3 and it was all the plotting functions. And at some point they split it in a different package because they realized that it's not only PyMC3 out of there, but also now TensorFlow probability and STAN, and the plotting in them is always the same. And no matter which engine are you using for the analysis of uncertainty. So basically this function, what it's doing is just taking from PyMC the output and just create the RVids object that now we can use to plot. So most of the functions that we're going to be using is, you can find them in GemPy. They are just a bit of a tweaking of RVids functions. And I already made them specifically to use them to teach these type of things. And so they are very verbose and very clear, hopefully. So the syntax that they have is that we are just creating this plot posterior object. And the first thing that we can do is just define which type of figure we want to create. For example, give the size. So 10 was good, I think. Size 15. So I have a few plots that eventually we're going to see all of them, but at the moment we are just going to use the marginal plot and the likelihood plot. Another question is, we can just give a specific argument for so var names. So which names do you want? Okay, I should deactivate compile. It's making it much harder. But yeah, I will do it later. I mean, some things much harder, others less. So this is again, I have a bunch of possible arguments. So for this plot, I don't want to use the trace, the credible interval is 92%, and the group is prior. And for the likelihood, so here we also add why we have to use to choose the iteration. And height. Okay, and the last argument, because will just be likelihood. Okay, so this plot is just the plot of the prior. So here is basically a representation of the guess that we have here in our left. So the mean of the things that we are thinking. So this in the x-axis, we have how much we think that is a reasonable range. So beyond 195 and 220, we start thinking that the probability of that is relatively low. But we are also giving uncertainty to how sure we are. So that is basically what this gamma function represents in the y-axis. So we are pretty certain that, well, this is basically giving you, when you are doing the inference, if you are very, very sure about your prior, then you can just remove this parameter completely, or you can just make most of the mass very close to 1 point. But here it's going to give you a set of possible solutions, some that they are farther from the observations, but because you think that the observations there are less real, or less true, let's say. But still valid, but to a point. And maybe it gets a bit more clear when we look to the posterior. And in the other side is completely different dimension. So here we are looking at the observations. So here is the observation that we have, the 2.1. And now we want to just put these things together. So our guesses, the plots of our guesses, and the observation. Now I'm regretting not just copying and paste all of this. So I think I'm going to just go out of this. Because actually plotting code is a bit boring. It's not worth being just looking at that. Exit presentation mode. Actually, here I have my cheat code. Now, because I've been spending already half an hour, I'm going to start speeding up a bit the content. Still, if someone is following and wants me to slow down, just let me know. So these are basically the same functions that we had before, but I have changed a bit the arguments just to see also the posterior. So now we not only have the blue representation, that was basically the distributions that we had defined before, we also have these red distributions. And actually this red distribution is the result of our inference. So this is basically how we morph our guesses depending on our observations. So in this specific case, because we only have one observation, one thing that we can look is that in the y-axis is pretty much the same, so the red and the blue. And this is because we cannot infer how the certainty of the observations when we only have one point. So we don't know. That's going to change completely when we're adding more. However, we definitely move toward one end is the likelihood. How much? So here is coming. So plot here at the right. The mean of crossing here is defined samples of how is by samples of the y-axis. So yes. If we just do here in range. We see have different bells here. So at the left, we are always plotting the same. So it is the blue is the prior, the red is the posterior. But in the right, it's different samples. So every single time, we are just sampling a value from our prior, so from the blue, which is going to define the shape of one of these curves at the right. And each of those curves at the right is going to have different likelihood functions of the observation. So the observation is always fixed. But the curve, so basically the normal distribution, the definition of the normal distribution, so because we are changing the mean and the standard deviation of this likelihood function, is going to be different every time, and every time is going to give you a different likelihood value. And this is going to and this is going to be weighted with how likely it is to sample, because when we are looking into the sampling side of things, obviously it's more likely to sample from the mean of our blue distribution than from one of the wings. But that is completely independent to how likely are the curves that we are seeing in the right plot. And now we have a bunch of, this is basically the whole full picture of Bayesian Inference. And now I have a bunch of plots and examples just to start bringing these ideas home. And so until now, the thing that we have to think of is we are defining a model that's basically defining the curves that define this blue area here at the left. We are going to have an observations, which are going to be fixed here in this axis. Sampling from the blue distributions is going to give you different curves, which is going to have different likelihoods, and then we have to weight all of these things together. And that is basically, in a nutshell, what is happening when we are doing an inference. And now by looking at different examples with more observations, a bit more parameters, hopefully we will see how all of this comes into play and how well this scale with parameters. Okay, so I'm guessing that there's no questions. Okay, so now I'm going to just repeat the same, but we are going to increase the number of observations. So if we go to our OneNote, so same example as before, but now we have multiple people just taking multiple measurements. And this is an interesting case because we are just measuring one single event or phenomena, but in the moment that you have multiple people measuring the same thing, you are going to get different values. And obviously, depending on how difficult it is, the measurement, the range are going to be different, but we are often having multiple values of the same phenomena. So I'm going to go away from presentation mode. Again, I think that I was too optimistic when I prepared this, so I'm going to start copy and paste a bit more code. I'm going to copy the next one as well. I was definitely too optimistic about how much we could type. All right, so now I'm going to go back to presentation mode. Same model, exactly the same prior. Again, this is the normal distribution that define the mean of the likelihood function, so this normal distribution. Now that we have seen the result, it's easier to visualize and to try to bring together the PyMC model with what it represents. Sigma is basically the prior distribution that represents the uncertainty of our data, so this blue distribution. And Y is a normal distribution that takes as mean the value of our mean prior, and as a standard deviation, the sigma of our sigma prior. So here is where these two things get connected. So this is this normal distribution, so the normal distribution that we see here, which is defined, the mean of this curve is defined by this parameter here, and the standard deviation of this curve is defined by this parameter here. And now has also this observed, which is the observations that we have that are the values in this axis. Same model as before, the only thing, the biggest difference is that now this is the list, so I have more observations. So I do the simulation, so exactly the same as before, just sampling the prior. So this is basically sampling the blue, because we are just defining the distribution, but just for the plotting, we are just taking 1,000 random examples. This is defining the red, so this curve here. So this trace is the important thing. So here is where we are doing really Markov chain Monte Carlo, metropolis in this case. Well, actually, no, I think that in this case we are using NATS, so Hamiltonian Monte Carlo, doesn't matter. And this is the posterior distribution that is basically once we have the posterior computed, we just sample it again. So this is the inference. Everything else is just for plotting purposes. And plotting is what we are doing. So this is just a plot of the observation dimension. So before it was just one red dot, now we have a batch of red dots. So that basically represent different measurements of the same phenomena, in this case, the thickness of that layer. And this is basically the last iteration. So this is one of the multiple possible families of curves, very similar as before. But one thing that we can see directly is that while before, I'm sorry for going up and down too much, if that gets annoying, just write it in the comments. But in the previous example, because we only had one observation, basically the thickness of the likelihood function, which in this case is a normal distribution, it was basically collapsing. So it was just keeping a bit of a bit wide because the prior that we were just giving here, otherwise will be completely collapsed in just one line with infinite likelihood. In the case that having multiple observations, the curve looks completely different. So now it basically envelopes all the observations, but now it's not so narrow. So this is a more familiar inference what we are doing here. And this is another type of plot that we are doing that I think that is quite interesting. So basically, this is an example of the first 10 iterations that we are having. So another way to see this MCMC probability or distributions, inference, sorry, is just start moving these likelihood functions, whatever they are. Then they don't have to be only normal, they can be any other type of distribution. But to start playing with the parameters of this distribution to start trying to fit the data. So at the beginning of the inference, because we don't have any information, we don't know anything. So normally they start in a random location. So like these two first curve, they are just there. But little by little, they start to get attracted towards the observations. And it's not only just attraction, because then it will be just an optimization, but also just making the standard deviation higher or lower, just trying to fit the data. So for example, you can have a curve like the third one that we see here, that is a bit shifted towards the red, so that all this bunch of points are falling on the high likelihood area. And then this is almost considered as an outlier. Or you can have curves that they are more towards the middle. So because for the course, we didn't want to be just sampling, taking too long, we just created some GIFs. So basically, the only thing you have to do is to remove this. So this is the inference. So how the whole MCMC chain is just sampling from the prior, evaluating likelihoods in every iteration. So this is the first 30 iterations. So at the beginning, the chain doesn't know anything about the observations, doesn't know where it is. So it's just sampling randomly from the prior. But then the likelihood values start to push the chain towards the observations. And once they reach to the area of observations, it gets there. This is a simple problem. Yes, having a bunch of observations, you can just solve this in multiple ways. But I think that it's good to visualize what is really happening there. So the priors define how we can wiggle the likelihood function, and those definitions are with probabilities. And then the likelihood function just try to, within the room that the priors allow it, just to find multiple options that fit the data and the priors at the same time.
You want to say a word about the color change?
Right. So actually, the color of the bells has meaning. So basically, the highest is the most likelihood, or the most likely bell, or likely, the most likely sample of all the samples that we have done so far. So at the beginning, because we only have one, they have the same color. But what we can see is that everything is getting darker. So basically that this, in comparison, the bells that they are appearing now, in comparison, they are getting more and more likely compared with everything else, until arrives that one that is much more likely than the rest. And it's important to see the change of colors, because that also gives you a feeling of that the results that we are getting from our inference are relative. And this is getting into math that I really don't want to get today, because I think that is more interesting to see things like this. But we don't have a way to explore completely all the possibilities. So we cannot get a perfect result. That's why we have to do some simulations. That's why we have to do MCMC. So it could happen that we are always missing another set of family of normal distributions that that they fit the data better, and then what values are very likely will change completely. Yeah? So that's why it's very difficult to give absolute values of our posterior. So it's always relative to what we have been able to search. So there are techniques to know how well we have searched the space, but could be always a configuration that we are not finding. Okay, so this same plot, a bit different. So this is the same plot that we were seeing before for this model. So now we have more observations, and because we have more observations, the prior of the standard deviation of the likelihood function that before was pretty much the same, so we were not learning anything because we only had one value. Now it has changed, because this basically really defines how wide the likelihood function has to be to fit the data. So, and that really depends on how far away our observations are. And another interesting thing is that now, because, and when we are looking here into the right plot, this is just one iteration of multiple. So normally it's the last one of all these iterations that we are seeing here in the GIF. But an interesting thing to see is that in the previous model, when we only had one observation, the mean value was shifting a bit right, because it was really just moving the mean prior to be on top of the observation. Now, because the whole model is more uncertain and the posterior is more uncertain, so the values of there is more information in the posterior, another topic that I'm not going to get. The posterior is quite centered with the mean in this parameter, in the mean, the one that defines where is the bell. Because basically the only thing that had to do the model, it was just to make the likelihood function a bit wider, and then suddenly all the values were fitting. So there was no reason to choose one mean, so one thickness mean over another one. So that, and because if we don't have any reason to choose something else, we were just defaulting into the prior. Okay.
There's one question in Slack from Astor. I have a question. The position of the initial model, I think he means the GIF, didn't matter and is usually close to the true model from the iteration number smaller than 10. Or does it depend on it?
Yes, let me check this GIF, because maybe I think that in this one we also have the chain, no? Yes. So again, another plot of the same event. Here, really me hammering all these things. So here appears the chain for the first time until now, and maybe has been a mistake of my preparation, because if it's an MCMC, it seems that the chain is important. So what is the chain? So in the end, the chain, the only thing that is representing is samples of our prior. So when we start an MCMC chain, so when we start the simulation to try to integrate observations and priors, we don't know where to start. So basically we sample randomly from our prior. And here when the chain starts, you can see it's close to the mean. So it's close to this area that is the most probable area given our priors. And at that stage, we didn't touch the observations for anything. It was really just all about our guess. And as I was mentioned before, that is going to give you this curve, and then the curve is going to start moving towards the observations, because that is giving you higher likelihood values, and eventually it's going to converge. And then once it converges into some location, then just start exploring. And then this is important because, I mean, once the chain converge, you cannot say that one solution is much better than the other. So you cannot say that thickness 2.2 is much better than thickness 1.8. So some of them, they are slightly more likely than others, but still you are within the range of possibilities. So that's where the uncertainty comes into play. I don't know if this GIF answered the question. I hope so. Any questions? So basically, this is really the simplest example. And I think that this GIF summarize pretty much everything that we have been talking until now. So again, just to reiterate and to summarize, and just giving a bit of time if someone has question. The blue functions are defined by us. The observations are defined by us. And then what we want is just see which area of the blue, and all of this is multidimensional, right? Because as you can see here in the 2D plot, in this case, because we only have 2 parameters, it's very easy to plot. But it's like this, which area of this blue zone fits the best all the observations that we are giving. And if our prior functions will be just uniform, so completely flat, then we will really just look in exactly which area it is of interest. But it's getting much more interesting when we are just given normal distribution, gamma distributions. And there is nothing special about normal or gamma distributions besides that they are mathematically very, very stable, and normally the methods work better, but you could use pretty much anything. What time is it?
5 to 5.
I have still another GIF, which I don't remember.
Like I have one with 4,000 iterations.
Yeah. So this is the same one. So before it was just the first 20 iterations, which is where there is more information and there is more change. But usually you do these chains for thousands of cases until they converge. It reaches a point that the red lines doesn't change. They are all in the same place. Because there are so many samples that when you are averaging over all those samples, that gives you something close to the real posterior. Okay, so if there is no questions, we can move to the rest of the tutorial. So I don't want to, my goal was not to get into mathematics, because I think for that, if someone really wants to dig into that, Michael Betancourt YouTube videos and blog posts are the Bible of all of this. So there you can really start digging into the math behind this. So something I wanted to show is how we can just scale this. So this is just a 2-parameter problem with just one set of observations. But a nice property of Bayesian inference is that to some extent, and adds out of complexity, you can really start adding more parameters and adding more observations. So I think that I will just post again the problems and then start moving a bit faster. I think that as I'm doing the course, I'm realizing that I think it's more theoretical than programming. So I really think I'm going to jump into the solve notebooks, so I don't have to spend so much time just copy and pasting. And if the course goes a bit shorter, probably it's even better. So, and then we can really just dig into the plots and try to understand how the plots relate to the PyMC3 models that we are defining. Again, so you can find both notebooks in the repository. So now I'm going to move to this one and go back where we were. Here. Okay, so back to OneNote for a second. So far we were just looking at one phenomenon, the thickness of this layer. But often we can have measurements, especially in geology. We have measurements of multiple data sets that they are related to each other, but they are related through very complicated mathematical functions. So here we are going to first mimic one, just escalating a bit this one, how complexity can start being encoded in more complex models. And then we will just have a short GemPy example so that you could really imagine a real case, a scenario. So back to this case. So now we had a group of students and one phenomenon. Let's think that we have so many students that we can use them in parallel. So here we have another group, and to this group we don't say just go and measure the thickness. We say them go and measure the location of this layer. And then we have another different group of students, and same story. We just tell them to measure the location of this layer. So in the end, we are going to end up with basically 3 data sets. So the data set of the position from these guys, the data set from the position of the other interface from these guys, and then another set of observation from these people. In this case, obviously, this is just crafted for the example, and you could just everybody measure the same phenomena. But there are cases that you really can only access to some specific data set for whatever reason. But we know that they are related. So in this case, it's obvious that if we subtract the top layer from the bottom, or the top interface from the bottom interface, we are going to get the thickness. So can we encode that in our Bayesian model? Yes. So we'll come back to here, to the code, and let's see how we can do that and what it means for our plots. All right, so here we are in the chapter extending dimensions. So same observations of thickness as before, but now we are increasing the complexity of the model. So before, we only had one observation, so one likelihood function, and 2 priors. Now here we can start saying that there are more stuff. So basically we have the mean of the top layer, so basically the mean of the location of the top layer, the standard deviation of the top layer, same for the bottom, and then for the thickness. So we could do each of these independent, and then will be basically the same exercise that we were doing before. But here there is this deterministic function that depends on the mean and of the top and the mean of the bottom layer. And for this likelihood function, basically what we are doing is just sampling from those means and doing an operation, mathematical operation in between. And then that is what it relates to the observation. So here the important aspect is the mathematical operation, because in this case it's very, very simple. It's just a subtraction. But in the moment that you get the concept that you can just apply any mathematical function to your priors to relate to observations, that opens a world of possibilities. So again, let's first define the model, run the model, and then we just start looking into plots to understand what we have been doing. So that was the definition of the model. Here we are doing the sampling. So sampling of the prior for the blue plot. So the blue shade plot, the trace, the red shade. And actually the posterior, I think, is the one that we are using for the red shade. We just move it to our bits. And first plot. So this is, again, yet another new plot. So before, we just had 2 priors. So it was very easy to plot in 2 dimensions. Right? So we have the mean in the x-axis, the standard deviation in the y-axis. Now we have 6. So we have the mean for the location of the top interface, the mean for the location of the bottom interface, and the mean for the thickness, because that was another thing that we had students guessing and taking measurements. And the same for the standard deviation. So now we have 6 parameters. So now it's a bit trickier to plot, but you have to think that this is scale in the same way. So in the same way that before we had an area, with 3 variables you are going to have a volume, and with 6 you are going to have a 6-dimensional space. So the chain that we saw before moving into D now it's going to be moving in 6 dimensions. This entails a lot because the posterior in respect with the prior space is getting smaller and smaller as you're increasing the dimensionality. Again, awesome work of Michael Betancourt to explain these things. But so far 6 parameters is fine. So it's easy enough for the chain to converge. And here we can see also something quite interesting. So there is, especially between the top and the bottom, it seems to be some type of correlation. There is like 2 hills. And this we can really just think that obviously when both layers, so both interface, go down, they have the same thickness. So that start correlating the priors. Anyway, so even if our problem now is high dimensional, we can still just plot in it as a cross section. So of this 6-dimensional space, we can just do a 2-dimension cross section that looks like this. But still, this is not the full picture. It's going to be a volume volume is 3D, so a space where the chain is moving around. But maybe coming back to here. So one thing that we have to really have clear is that the value, so these red curves that we are seeing here, this posterior, they bring information from the full model. So if we remove one of the data sets, they are going to change. So this is really how likely are the different iterations, which again, in every iteration, we are just moving our likelihood functions around, so wiggling the likelihood functions, if you remember. And in this case, because now we have 3 data sets, there are going to be sometimes that one iteration fits very good one of the data sets and very bad another data set, and others that they are going to fit very well the 3 data sets, and those are probably going to be the most likely values. So in the end, this is an integration. So MCMC is really just an integration of all these probability functions that we are using to define the priors and also to define the likelihood function. Okay, I'm going to try. Sorry for that. Okay, maybe I can just open the usual view of the Jupyter Notebook just for a interactive plot that I have here that may help us. Yeah, there you go. So here, basically, I can just take a cross-section of the distributions of the prior, the prior and posterior, so the variables that we are using in our problem. In this case, I have chosen the mean from the top interface and the mean from the bottom interface. And this is a bit interesting because they are correlated. But maybe also now that I have the control and it's not just a GIF, we can just go a bit back. So this is the definition of our problem. Again, we are just defining these blue curves. In this case, we are seeing 2 out of 6. And that is defining a space, which in this plot, we can see the 2D cross-section of a 6-dimensional space. And we are also defining all the observations here that we see in the likelihood plot, which I think I have a back in one of the plots. And now we are trying to have to integrate all of this. So basically finding the areas in our blue space, the areas that fit the best the observations. And for this, we are using the chain. There you go. No.
Kernel died.
The kernel crashed. Yeah, it wouldn't be a transform workshop.
But it's back on again.
If the kernel doesn't crash. I'll try again. If it crashes again, I will just move on.
Crashes in early iterations. So if you start from iteration something like 10 or 15, then it should be fine.
Okay. So Jan is telling me that it's crashing when this is probably one of the functions to compute the plots, that if there is not enough iterations, it crashed. So we will miss the first iterations, but I think that we can just imagine. So here is the 10. So as we saw before, in the first iteration, we were somewhere down there. And the chain, and this is basically the mathematics behind the Markov chains and Metropolis algorithm that is attracting the chain towards the areas with observations is moving over there. Eh? So, and again, each of these iterations, we are just sampling from our prior space. So in this case, we have sample from this point from the mean top and this point from the mean bottom. It's more likely to sample from the areas with higher probability than from the wings of our blue functions. And I'm not sure which likelihood function I'm showing here. Yeah, so the likelihood function of the thickness. So we are subtracting these two values, and that is going to give us the mean of this normal distribution that we are using for the likelihood. So basically the location and the standard deviation. So basically how wide it was this normal distribution was also a prior that now we are not visualizing that exists there. So again, going through the whole process, we sample from the blue. That's going to give us one curve in the likelihood function, and then once we have the curve, we evaluate all of our observations, and then we just multiply the value of the likelihood function. Again, I don't want to get into math. That's basically the math. So all these red lines that we are getting here, the value of the likelihood, we just multiply it, and depending on that value is going to move the chain, or is going to accept the move of the chain. Otherwise, the chain will go somewhere else. And that's how the chain is getting attracted to the areas of high likelihood. Next iteration, we sample again. Now it's really almost in the middle. That is going to give us another location of the likelihood function, which is very good to look into the joy plot to see how really they are moving from the left towards the right. But eventually the chain is always going to be just moving around that space, the space where really converge, where the probability is mostly equal. So the probability of sampling from the prior and the likelihood of evaluating that balance the location of the chain so that the chain can be moving all the time around the same area. Good. I hope that it was worth it. Yes, I mean, so making this plot is the reason why I could not just shape an environment that it was easily working. So I hope that at least they are helping to get a bit of intuition. And another view, I mean, there is a lot of content about what is MCMC in YouTube. So here I just wanted to just give yet another view and another intuition about it. And also another spin, the spin of geology. So maybe now I will just go back go through the last example. Well, first, any question?
Not yet. No, I answered one in the thread, which was just a follow-up question.
Good. So all of that, they were my toy examples to try to give away the intuition of how priors, likelihood, and the chain in between is connecting everything. So now using a very similar logic, so thickness and observations and guesses, I can show you how this could be applied in a real case scenario. So in this example, we are going to use GemPy, although the geological model is very simple. So for the people who don't know, there's a GemPy is a Python package to do interpolation. So of geological structures, you can have unconformities, you can have faults. We have a pretty extensive plotting API, and also has this probabilistic part that sadly I never had time to really write good documentation for people to use. We are working on it. It's getting there. But here we can see at least one example of how we can just combine what we have seen of using PyMC to just try to integrate guesses without observations. How to use that in a realistic context. So I think once again, I'm going to wait for the plot to explain what we are seeing. I'm going to go to the usual notebook because here PyCharm is doing some weird stuff. Yeah, so I think that here we can see it better. So this is our setting. So we are going to have thickness involved as well, but in this case, it's not going to come from students just looking to an outcrop. It's going to come from boreholes. So here we are just depicting two boreholes, and we have a couple of interfaces. The blue interface up there, the red interface there. Another observation that we are going to use, which seems completely decoupled of these geometries that we have been discussing, is gravity. So here where the computer has frozen.
That's the monitor thing. Just close the video. Close it. And close it up again. And that
Okay. I think I'm back. Sorry. So the screen just got frozen for a second. Oh man, don't do workshops when you are on the road with poor equipment. Again, as I was saying here, we're going to have a gravity device that basically is going to give us a signal of gravity of the model. By just using GemPy, we are going to really relate all of this. So the location of our interface, observations of thickness, and observations of gravity. So the function that I just ran up here, it was just to set the GemPy model. I'm not going to go through it. In the tutorial of last year, it's everything about GemPy, and we see what all these functions mean. Okay, so now I know what is happening. I have this matplotlib backend. So here we have just the zenithal view of the same. So just to see exactly where the device is. So I just put the device in the middle of the model, nothing too fancy. Yeah, so now we are just interpolating the model with GemPy. And now we are using just GemPy functions to just see the whole space interpolated. So this is happening in 3D. For the tutorial that we are looking at the moment, it's not interesting. If you are interested in GemPy again, so I have the last 2 workshops I did in Transform. It was all about that. Okay, so this is our setting. So this is what our first guess. We just have some observations of borehole. We just take it. We just interpolate. Well, we interpolate, and also we calculate the forward gravity. So in GemPy is built in a forward gravity function that basically you can say put some location and give some density to each of this layer, and you just get the gravity response, the simulated gravity response. And from this plot, here I have a couple of functions, but obviously you can also imagine, so here is flipped 90 degrees, but this is basically the thickness of the blue layer. So easily, just by counting voxels and knowing how big is each voxel, we can also just estimate the thickness. So yeah, it's very similar to all the previous examples that we were seeing. So we have some input points, in this case, the location of the interface of these points in the boreholes. And then we have a bunch of observations. So observations about the thickness of the blue layer and observations about the gravity. Can we just do a Bayesian inference to just try to get a set of plausible models with an attached likelihood? Yes, we can. Spoiler alert. That's okay, I'm going to try to run this, but
I think we didn't run the gravity.
yeah, so this is basically a manual example for me to simulate what the chain is going to do afterwards. So the chain is going to be just moving these 4 points that we are seeing there. So the red dot is the grid that we are using for the gravity, not important in this case. This is the gravity value. So for this specific model, we are simulating 356. And if we just change the location of the blue layer, so just making, I don't know, this is the red, just making the red layer higher, we change the value of the gravity. Yeah? So basically, we have parameters that we have a mathematical function that relates the observations to our parameters. And that mathematical function is really, really complex. So before we just had a subtraction for the thickness, now we have a full Gaussian process going on there, and then just mapping voxels to densities, and then just apply the gravity to each of the voxels and something. So as long as you know the mathematical function that relates your priors to the observations, you can just go as crazy as you want. Yeah, and basically here is going to be a bit of code that I think is not interesting to get into the tutorial of today, because again, I think that this is ending up to be more about the theory than the programming, with a nice example for you to play with. But here we are just extracting indices of the arrays that GemPy contains, the inputs, and here doing a bit Theano wrapping, so just taking normal Python functions and wrap it with Theano code so that we can just put it in PyMC3, because PyMC3 is working on using Theano as backend. There is a possibility of using GemPy directly with the Theano graph that is giving you gradients. That definitely is really, really advanced use case. But if someone is wondering, yeah, you can use GemPy directly into the PyMC3 model. Similar to before, defining our observations, a bunch of gravity observations, a bunch of thickness observations, because those are observations, and now defining the PyMC model. So despite the mathematical model being very complex, the Bayesian model is not that complex. So we are going to have a normal distribution that represents the mean of the 4 points that we have. So this is the syntax that PyMC has to create 4 distributions that they are exactly the same. So you can instead just type in every single prior manually, you can just define all the family of normal distributions of your model just by using NumPy arrays and defining here the shape. So in this case, we have 4 points. That is the 4 interface points that we saw before. And now I have a couple of deterministic functions that they are calling the GemPy code to just give you the gravity. Here they are it's calling the GemPy code to give you the thickness of well 1 and the thickness of the well 2. Well, actually, the array. The thickness is just the sum of the array of the well. And the rest is again, very similar to what we saw before. So for each of the observation groups, we are just creating a standard deviation that this basically defines how wide is our likelihood function. So in the plots at the right, how wide it was the bell. And now in our observation, so when we are defining the likelihood itself, so the parameters that they have, this observe argument, we just said what variable contains the value that defines. So again, so here in the case of the gravity, if you remember, we are going to have, in the x-axis, all the observations of gravity, and then we are going to have a normal distribution, because here we are defining normal, that we are going to be moving it right or left, and it's going to get wider or narrower. So moving right or left is going to depend on this, so on the gravity that we are simulating and the comparison of the gravity that we are simulating with the gravity observations. And how wide or narrow it's getting is how, depending on the location of the bell, how well it fits all the observations. And same story for thickness. So again, in the end, it's very similar setting as what we were doing before. The only difference is that before we had just a subtraction between the top layer and bottom layer. And now we have just a really complex function called in one library, but in the end is giving you a value. In the same way as before we were getting the simulated thickness, now we are getting the simulated gravity and the simulated thickness in one well and in the second one. And this model, you have to run it quite a bit. So I have here the results. So if you run this, you have to run a couple of thousands. So it takes like 10 minutes. And you can start feeling how speed of computation, number of variables start to play a huge role. So the limit of how complex you can go in a Bayesian inference nowadays is given by computation. The longer it takes to evaluate one sample, more time it's going to take. And eventually, very soon, all those numbers start adding up and you have to really simplify your model. But yeah, so if we just look to the first plot, after running the simulation, so this is already the plots. Well, this is the plot of the prior. So basically here we will see exactly the same curves as we have defined. One thing that you can see is that when you don't use too many samples, the curves are not perfect, because in the end we are just approximating normal distributions just by sampling. So you really need to go into tens of thousands to really start getting those smooth normal distributions. But basically, for example, if we just take depth 0, this is a normal distribution center in around 3000, between 3000 and 3010, which if we go all the way here, it was basically the location of this point, and it was the location that we used for the mean. So here we can just really see the prior predictive. So for our priors, they are just sampling, but we can also see values for our gravity and from the thickness. So these values are basically from, if in our problem we don't use any observations, we are just defining some normal distributions to our parameters, and we sample, and then we just compute the gravity and the thickness. This is what is giving you. So gravity is giving you a range from minus 360 to 348, and thickness hopefully always positive, and also difficult to value. So this is an interaction between all the priors. But this is only half of the story. So this is just error propagation. So we are just, our mathematical model has some parameters, in this case, the location of the interface. We just make them stochastic. So we just say that they are just probabilistic, and then we just sample. So this is pure Monte Carlo. Here there is no MCMC. It's just sampling from your priors, running your model, and then you just get the distribution of your gravity. If we include the observations, and here you can see that in the function that I'm calling to run the trace, I'm already saying use Metropolis because it's not only Monte Carlo. And again, this is the one that is taking a bit. So in my computer, it was taking 18 minutes to do 2,500 simulations. But it's giving us the posterior. And so again, this is analogous to the previous one. So those red values is also in, or those orange values are integrating the arrays that we had in exactly the same way as in the previous examples. So as the mathematical model is getting more complex and you have more variables, it starts to get trickier and trickier to follow every single step as we were doing before. But if everything works out fine, it's happening the same. So in this case, these are the posterior of our model, and then you can see the gravity and thickness that technically they are not posterior because they are just result of the location of the depths. So what I mean is that if you have the depth 0, depth 1, depth 2, and depth 3 variables, and you sample from the orange distributions, and then you run your models, then you can just reconstruct gravity thickness and thickness 2. So gravity thickness and thickness 2 is always depending on your variables, obviously. Same for the posterior, same for the prior. But yeah, no, here we can see how there is a subset of values. And here we cannot see it, but actually in the thickness you can see it pretty good. Start to be some correlation. And for the correlation, you need a different plot, but you can start imagining that in this case, just to keep the gravity more or less equal, either the thickness stays the same, or if the layers start going deeper, then the thickness has to start going a bit higher. So all these parameters start to get correlated, and that is information that you are getting, or actually information that you are reducing of the system. So these are the type of knowledge, some type of correlation hidden in your model that you didn't see it before, and that if you treat it independently, you cannot see it. Anyway, so this was just to show a real case scenario, just to show that it's not just about having one event and just putting a bunch of normal distributions around. And this can scale at least to this level, and with a lot of tricks, you can scale it much more than this. But also, again, this took 20 minutes, so you start hitting some limits, and so you need to start using better samplers. So using gradient-based samplers that they use the gradient of the posterior to move better. So you need less iterations. You need to optimize your mathematical models that they take as little time as possible, but still this stays more or less the same. Okay, so I mean, we had 2 hours allocated. Has been a bit unfortunate workshop because we were not in our perfect setting, so it was a bit tricky for me to just code live because I don't have a second screen. But still, I hope that the notebooks are there. The channel is going to be open, so if anybody had any questions, just please contact us. And at least I hope that it gave you a different view of what is MCMC, a bit of a different view than what you find if you just type that in the internet. So if there is no more questions, I think now we can just keep it short, this workshop. Steve? Maybe I've been talking alone.
The screen looks nice. Stream is still running.
Okay, so
There are no new questions in the Slack, so I think
Hello, Miguel.
hello.
I think you're all done, correct?
Yes.
Yes.
It's already losing.
Excellent. Well, thank you very much for a great tutorial.
It's been a pain, definitely. Doing in a different computer in a wrong room, but yeah.
Yeah. No, but great. Thank you. And we just everybody, please come to the Slack channel for follow-on questions, and you know where to find Miguel and Jan on the on the Swung Slack.
Yes, definitely. So this is just an introduction, but this can be an ongoing discussion. And definitely for the people who is waiting for the tutorials on probability and GemPy, they are coming. Hopefully this year, so that then we can really just all the stuff that we have been talking about, just making proper documentation that people can just go there and check.
Excellent. Well, great. We'll look forward to it. Well, thanks again. And everyone, please check in for the next tutorial and enjoy the rest of Transform.